this is probably the most important lecture of the entire semester. What we're going to do today really introduces a key idea that really we're going to spend the rest of the semester understanding, expanding, making comparisons with, and whatnot. And the goal of what we're going to do here, what we want to be able to do by the end of the semester, is to predict the behavior of any system, no matter how complicated it is. So it could be an electron or it could be a cluster of galaxies into the future in some open-ended way, arbitrarily far into the future. Predict exactly how it's going to move, where it's going to be, what it's going to do. So that's our goal. And the first important step is to introduce and explore the momentum principle. This is our first fundamental principle, and it's what we're going to do today. We've already talked about the idea that what we do when we're analyzing the behavior of something is to divide the world into two pieces. So we pick some object or collection of objects to be the system. That's usually the thing whose motion we want to track. And the rest of the world, everything else in the universe, is the surroundings. And an idea that we've introduced and explored qualitatively is that the momentum of a system, whatever we've defined as a system, changes only through interaction with objects in the surroundings. Otherwise, as Newton observed, our system is going to keep moving at constant speed in a straight line forever. A special case of constant speed is sitting still, so that's fine. What we want to do today is make this quantitative. We want to be able to calculate precisely where how the motion of something will change, and by extension where it's going to be at some time. And so we want to have a quantitative way of talking about the interaction of a system with its surroundings. And not surprisingly, this quantitative measure of the interaction of a system with the surroundings has a name. It's called force. This is a familiar word. And a force exerted on something by an object in the surroundings, it's a vector, because forces have magnitudes. That's how big the force is. And they have directions. So go that way or that way, up, down, left, right. So it's a vector. It's written as an F with an arrow over it, of course. And the unit of force in honor of Isaac Newton is a Newton. So it's measured in newtons. And it's abbreviated N. And it makes it easy to remember about what a Newton is, to realize that the magnitude of the force exerted by the Earth on a small apple is about 1 Newton. So the famous apple that fell on Isaac Newton's head did so under the influence of a force of about 1 Newton. And of course we would write this as 0, -1, 0 newtons in our standard coordinate system, where x goes that way, y goes that way, z goes that way. How do you measure forces? Well, you have to come up with some scale to measure forces. And one simple way to do it is to measure forces of reasonable magnitude is to use a spring, just an ordinary spring. Because it turns out that if you pull on a spring with a certain force, it stretches a given amount. If you pull on it with twice the force, it stretches twice as much. So a spring is a nice linear scale for measuring forces. And of course, we've evolved many other devices to measure forces along the way. How do we draw forces? Well, of course, we represent them with arrows. And the arrow has a direction, which indicates the direction of the force. Its length is proportional to the magnitude of the force. So if we drew the force of the Earth on this apple, we would draw an arrow down, we always put the tail at the center of the object, the length of the arrow proportional to the magnitude. And forces are often labeled by the kind of force. We want to be very careful to keep ourselves honest by also labeling forces with the name of the object and the surroundings that exerts the force, because that keeps us from inventing forces that aren't real. So we could call this a gravitational force, but we would put in parentheses that it was due to the Earth. And so there's our apple. Now, there's a very important concept that goes along with forces, so that's not a very hard concept, which is the concept of a net force. The term net has a very specific meaning in physics. And what it means is, it means the total. It means the sum of all contributions to something, whether they're positive or negative. And so when we talk about the net force on something, we're really talking about we have summed up the forces on this object due to absolutely everything in the surroundings, and there can't be any other forces in addition to the net force. We've added it up, and that's what there is, so that we've really taken account of everything. So this is gonna be a key concept. And not surprisingly, it's the net force, the total force on the object due to the surroundings that changes the behavior, changes the motion of an object. So, for example, here are two coffee filters, same mass. Okay. Now they're interacting with their surroundings in various ways. I'm going to let go of them and let them fall. But I crumple this one up. They still have the same mass. I drop them. They behave quite differently. And because their motion changed in different ways, we're going to conclude that the net force acting on this coffee filter due to the surroundings and the net force acting on this coffee filter due to the surroundings are actually different. So let's think about the force, the objects and the surroundings that are exerting forces on these coffee filters, and see if we can think through a little bit about what must be going on. So here's coffee filter 1, and here's the crumpled up one. So the system is the coffee filter. What objects in the surroundings are interacting with it, exerting forces on it? What's one object? Gravity is not an object. The Earth. The Earth. So the Earth, someone said the air. Absolutely right. Acting on both of them. There are lots of other things exerting forces on these coffee filters. Any object with mass exerts a gravitational force on any other object. So, in addition to the Earth, the moon is exerting forces on them, Venus, the sun, the person in the front row, the table. But those forces turn out to be fairly small. And so these are the main things. So it seems clear that somehow, do you think the force by the Earth is different on these two coffee filters? Probably not, huh? It's probably just proportional to their mass. So it looks like the force of the air on these two coffee filters must be different. And we'll be able to explore things like that in a little bit. So the basic idea is, how do we use the net force on an object to predict its motion? And we can write down the idea that Newton stated quantitatively in his force law, qualitatively. We can state it quantitatively. The basic idea is this, though. What we want to do is predict the momentum of the system at some future time, the future momentum of a system. Coffee filter, spacecraft, baseball. And it depends on two things. It depends on the momentum of the system now, and it depends on the net force on the object due to interactions with objects in the surroundings, and how long the force acts, so acting over some time. And these things turn out, this quantity, so the net force times the time, actually has a name. It's called impulse. And impulse is something that you probably have an intuitive feeling for. This car currently has momentum 0. If I exert a force on it for some time, it acquires some momentum. If I exert a force on it for twice as long, it acquires more momentum. So, wow. So, and if I exert a bigger force for a short time, still going to acquire more momentum. So, it's the product of the net force and the time, or the impulse, that determines what the future momentum is going to be. These two things are equally important. And most of the mistakes that we tend to make in reasoning about what the momentum of a system is going to be in the future are due to forgetting to take into account one of these things. So we're going to try very hard not to forget. And we can write this down as an equation. We can say the momentum of an object in the future is going to be equal to the momentum of the system now plus the net force acting on the system now times the time through which the force acts. And this is the momentum principle. Now we're making, in writing it this way, we are making an assumption. We're saying we're taking the force now, measure the force now, and we're assuming that it doesn't change very much during this time delta t. So if we're going to measure the effect I have on this fan cart, we're going to assume that I pushed with a relatively constant force for a short time. And it's not a bad assumption. If it turns out to be a bad assumption, we're going to find that what we're going to need to do is just take smaller time steps and do this repeatedly. So this is the momentum principle. This allows us to predict the future of the universe, to predict the motion of the world. So it's a very important and powerful principle. Now, we know that momentum has units of kilogram meters per second. We know that force has units of newtons and time has units of seconds. And we can only add things that have the same units. So it must be true that 1 kilogram meter per second is equal to 1 Newton second, which suggests that a Newton can also be written as a kilogram meter per second squared. That's breaking it down into the fundamental SI units of distance, mass, and time. So we can use this equation to calculate things. And I think you can actually calculate some things without being shown how to do it, because you know how to use vectors. So let's see if we can calculate something here. So we have a hockey puck sliding along the ice. It has nearly constant momentum of 10.05 kilogram meters per second until it's suddenly struck by a hockey stick. The hockey stick exerts quite a big force, 2,000 newtons in the z direction, but for a very short time, about 3 milliseconds. So what's the new momentum of the hockey puck? So what we're going to do is we're going to use this equation to calculate the new momentum of the hockey puck. So which of these quantities in this equation is the unknown? Future momentum. We know the momentum now. We know the net force. Do we know the net force? Is it fair to assume that the stick is the only thing that really is interacting with it? It's the only significant force for that 3 milliseconds. Absolutely. It's such a big force that other forces around are very small compared to that. So it's, for a very good approximation, it's a net force. Okay, so let's see if you can calculate it. Wow. Okay. Pretty nearly unanimous. And good job. So what you did, presumably, was simply use the momentum principle. So you said P future is the current momentum, which was 10.05 kilogram meters per second, plus the force, which was 2,000 newtons, times 3 times 10 to the negative third seconds. And so 2 times 10 to the third times 3 times 10 to the negative third is 6. So that comes out to 0.006 Newton seconds. We add that to that, and we get 10.011 kilogram meters per second. So good. You can do it. Now notice that there's a couple interesting things to note here. One is that one of the things this vector equation tells you is that a force in the z direction can only change the z component of momentum. It can't change the x component or the y component. And that's why we can use vectors to write these things, because it works that way. It would be much more complicated if it didn't work that way, and a force in the z direction changed the x component of momentum. That would be very messy indeed. So we should be glad that that's true. It's true, of course, in all other dimensions too, so that if I throw an object in the negative z direction, the gravitational force changes its momentum in the y direction, but it didn't change its momentum in the x direction. Now, the air might have exerted some influence in that direction, but a force in the negative y direction can't change the x component of momentum either. That makes our lives very much simpler than they might have been, so we should be very grateful for this. Okay, so calculations, no problem. It's also the case that this equation, we can use this equation even without numbers to reason logically about what might happen or what things are possible and can happen. So, for example, let's make a table of, here's the future momentum, here's the momentum now, and here's the net impulse, F net delta t. So, suppose we say that the net, when we add up all the forces acting on our system, they add up to 0. There might be force this way and a force that way, but they're exactly the same magnitude, so it could add up to 0. And let's say we think that the momentum in the future, the momentum of the system is going to be 0. It's going to be at rest. Okay, is that possible? Well, we look at this and we say, okay, if this is 0 and this 0, this would be a possible thing if the momentum now is what? 0. Okay, so that works. 0, that's good. Suppose I say that the momentum in the future is 0, the net force acting on something was 0, but the momentum now is not 0. Is that a possibility? It's not, is it? It's just not possible from that equation, so we can rule it out. Okay, let's think about the other situation. Suppose that the momentum of an object in the future we think is going to be 0, and there's a net force of 0 acting on it. What has to be true here? So if this is non-zero, yes. So this has to be non-zero. If we write this is not 0, this is 0, but that's 0, well, there isn't any way that can happen. We can't add 0 to 0 and get something that's not 0. So we can actually rule out possibilities without actually doing calculations. So here's an example of this case. Here's our system. Its momentum is currently 0. The net force on it due to the surroundings, well, it's not accelerating toward the Earth, and it's not going up, so it must be 0 in the y direction, nothing happening in the x direction. So the momentum's 0, net force is 0, net impulse momentum in the future is 0. That's an easy one, right? Let's see. Okay, we decided that the net force in the y direction must be 0. Let's think about starting now. Was that an example of this? Well, it traveled at nearly constant speed, didn't it? Okay, so we're going to start our time after my hand stops interacting with it. So it is certainly the case that during the period so here's another case for us. P, oh, that's dying, okay. P future, P now, net impulse. Let's talk about it while I'm pushing it. It's going to start from rest, but I'm going to give it a non-zero impulse. I'm going to push it with a non-zero force. And delta t is the time I'm pushing. Okay, so that's the time I'm pushing. So it'll take a little longer. Okay, at the end of my push, it was moving with a non-zero momentum, wasn't it? So we started from 0, gave it a non-zero impulse. Now, an important point about this, though, then we're going to take another delta t from the time my hand stops touching it. So then it's got this non-zero momentum. So here's the push. Starting now, it's traveling at nearly constant speed. Now, it isn't perfect, is it? There seems to be some friction, so it's slowing down a little bit. But if there were no friction, it would be the case that it started with some momentum P after the push, and a second later it had nearly the same momentum. And so that suggests that the net force must actually have been 0 during that time. Now that bothers a lot of people because people say, no, it wouldn't have gone anywhere without your hand. You don't push it, it doesn't move. The beauty of the momentum principle is that all of the history of the object is added up into the momentum now. Because what's the momentum now? Well, that's the momentum at some past instant plus F net in the past times delta t. And we can just keep playing this movie backwards forever, right? So the momentum of this object currently is 0, but it hasn't been 0 for the whole time the object existed. In fact, I picked it up and I moved it up, I moved it down, I moved it around, I put it down, I pushed it this way, I pushed it that way. It's had lots of different kinds of momentum. But when I stop interacting with it, whatever the momentum it's got, it's the sum of all these impulses in the past, added up and added up and added up, so that the entire history of the object is now added up into the momentum it's got right now. So, and it's really a good thing. We don't need to know everything that happened to it in order to predict its motion. Because if we had to know that a minute ago it was going that way, but then I stopped it and I moved it that way, it would be hopeless. We'd never be able to predict the motion of anything. So the fact that all the influences in the past, all the pushes and the pulls and the forces, the speeding ups and slowing downs and turnings have been added up into the momentum now, lets us just say, okay, this is very simple. All I have to do is count what's interacting with it right now. I don't have to worry about anything that happened to it in the past. I just have to count what's acting on it right now, and I can predict what's going to happen in the future. So that's a very powerful thing.